Right. Little notification that we are live. Welcome everyone to our webinar, 5 Ways to Improve Your LiDAR Workflows. We have a big team of people here working behind the scenes to bring you some amazing content. So we hope you're gonna enjoy it. And with that, hang on one second, I'm gonna get my slides set up. I am going to go and pass this over to Dale.
Thanks so much, Stephanie, and thanks everybody for joining us today. You know, my name is Dale Lutz. I'm one of the co-founders of Safe Software, and we've been at this for closing in on 28 years. And in that time, one of the things that I've cherished the most is the amazing characters that I've had the chance to work with, whether it's the various team members of Safe who amaze me daily, and you're about to be amazed by what you'll see today, or the characters that we've crossed paths with in the industry. And truly, we have had the chance, because of where we sit in the food chain, to cross paths with absolute giants in the industry. And so it was with a heavy heart this week when I read the news that I first didn't believe, that Martin Eisenberg, an absolute genius and active, influential member in the point cloud and LiDAR processing community, had passed on us. And the world is truly worse off without him. He made huge impacts in workflows. And if you're on this webinar, you care about LiDAR, you care about point clouds, your work has been impacted by Martin, whether you know it or not. He played a key role over the years in the evolution of the LAS file format, which many of our demos today will touch on or use. Much of the data that you probably consume is in that format, and Martin was a passionate defender for what was the best. And those of you that saw those arguments take place know about his passion. He also was an amazing algorithmic mind. And so the LASzip format is a very, very compressed way of storing LiDAR, which can be very, very large in data volume. He made use of all kinds of his own insights to squeeze that data down to the smallest possible. And then there is the LAStools set of utilities, and Kaylin and Richard are going to show some of those today as they look at how we integrated those with our FME product. And Martin actually came to our office and worked closely with Dimitri, who's on the call too, to make that happen some years ago. So thanks, Martin, for all that you did and for the amazing impact you've had. And we really hope that one day our paths do cross again. Ooh, and with that, I'm going to hand it back to Kaylin and get myself a Kleenex. Thanks, everybody.
So thanks, Dale, for doing the introduction. So I'm going to be presenting with Richard Jovita, and then Dimitri's going to be on QA. So on the agenda for today, we're going to go over a brief LiDAR overview, and then we're going to go through 5 ways to improve your LiDAR workflow. So everything from translating between formats to integrating with 3D city modeling. And hopefully, if there's time left over, we'll have Q&A. So the LiDAR overview. What is LiDAR? So LiDAR stands for light detection and ranging, and it's typically used to collect and create point clouds that represent or describe a surface. So FME supports quite a few point cloud formats: E57, POD, LAS, XYZ. Could probably name off the whole alphabet there, but if you did want a full list, we have a format matrix on our website, which you can go and filter by point clouds and LiDAR, and you should see them all pop up. So why do we use point clouds? We use point clouds because they produce amazing 3D visualizations, and they can really accurately represent the real world. And when we're working with spatial data, that's kind of something we are looking for. So the problem with point clouds is they can be huge, and they're kind of complicated if you're new to working with them. Some people claim that they're easier to work with than rasters, but starting new can always be difficult. They take up a lot of storage, they can be computationally expensive, and there can be limitations. So whether that's your computer or storage or knowledge. Most of our demonstrations will be done in the FME desktop, but I think Richard will be automating an example with FME server a little bit later on. So what can you do with FME in your point clouds? So you can create surface models, you can filter, reduce noise, clip to a specific region. There's a ton of things that we can do with our point clouds in FME, and today we'll be going over a lot of these examples. So the first step in improving your LiDAR workflows is to simplify the process of transforming and integrating point clouds using FME's point cloud transformers. So we have about 24 or 25 point cloud transformers, not including the ones on the FME hub. If you can see, this attribute manager has a rank of 2, and we did try and choose the most popularly ranked point cloud transformers to showcase. We have a link to our FME transformer gallery, which I think we can link out now. And if you filter by LiDAR and point clouds, you should see the full set there. So jumping into the transformers, the point cloud property extractor was one of the highly ranked ones that we saw, so we decided to showcase it. This extracts the properties of a point cloud feature and exposes them as an attribute. So here I'm retrieving properties of a point cloud's XYZ components, and then you can see Workbench nicely formats these into attributes, which we can work with in a more tabular manner now. So the second one is the point cloud combiner. This transformer name's pretty intuitive. It combines multiple geometries into a single point cloud. So here I'm combining 2 input point clouds to create one point cloud data set, but you can also combine this with other formats, so like SketchUp models if you had them. And I didn't add a screenshot of the parameters because everything in this parameter was left as default to get these results. So the point cloud thinner, this workflow piggybacks off the last one a little bit. All I did was add a point cloud thinner before the combiner. And so what this does is that it reduces data volume by identifying a set or interval of points to keep, and then it discards the rest. So I chose an interval of 100 here. It's pretty drastic, but this way you can kind of see the results. So you can see what it's doing. And this brings us to our second step in improving your LiDAR workflows. So to prepare your data. So although we have a ton of point cloud specific transformers, we also have a lot of other transformers that are point cloud compatible. So the tiler, if you're working with really large data sets, the clipper, if you have Z values, you can do cubic clipping. The tester, attribute managers, or creators, reprojectors all work with point clouds. And so in this screenshot here, all I've done is used a color setter to overlay a GeoTIFF onto the point cloud just to kind of make it look a little bit prettier. And then I downloaded a building shapefile for the same extent and clipped the buildings from the original point cloud, which is what you're seeing here.
So we're gonna create and automate surface models here. And this webinar portion is just gonna be talking about how to get yourself up and running if you're new to FME, if you are new to point clouds, and talk a little bit about FME server. So I wanted to go through how FME interprets the point clouds. FME interprets everything as one feature. This allows us to process it very quickly, but you still have your components on your point cloud. So each individual component will have its own values, and then you'll have your attributes for the entire point cloud. You can kind of see this here in the properties dialog of FME Inspector. You can see the individual components down here, and then you can see the component values. And you can alter those as needed if you want, or you can add in additional attributes which can be turned into components if you want to put a component across the range or a subset of the points. So when we're creating workflows, we're working with really big data sets generally. So we want to find out a best way to either thin it, clip it, tile it, bring it down that size so that we can work with it manageably in our workflow. And presumably your data, since it's all going to have the same schema, we should be able to work on a small subset and work through each transformer and then apply it to the greater set. This is just going to speed up the process of us designing these workflows. So it's always a good idea to have it in there. And then finally, when you're processing it, you might want to chunk up the workflow, especially with something like the tiler, where you can head off different sections at different times, or even on different workspaces, so that you can really utilize your full suite. So we'll jump in here with a demo. So this is the workspace, and I wanted to really highlight how simple creating a digital elevation model is. We've got some points here, and I'm going to go talk about this later, but essentially we're just grabbing some JSON points that will be integrated with FME server. So it's just an area that we're clipping the point cloud by. We're also going to clip a raster. And then the meat of this is we have a surface modeler, and that's what's going to create our digital terrain models. And then I also have an example down here, and we're going to zoom in a little bit, and I'll talk about this in more detail in a second. If you don't have classified data, so we'll run it through. And we get out a digital terrain model where we've applied the geotiff on top of it. So produces this fairly nice model. Jovita is going to go into more detail about how to get those buildings to look perfect based upon the perimeters, the building outlines. We've got your digital terrain model with your classified data. And then if you have unclassified data, we're going to go through a little bit of a method to pull out the bottom and the floor, the ground surface of your data. So creating a digital elevation model is as simple as adding one of these transformers. We have the TIN generator and DEM generator, but we've also got the surface model, modeler, which does a bunch of things. The nice thing about it is you're not going to be using all those factories and all those processes if you don't have anything connected. So it's not going to take a lot of more resources, but it's all there in one. The main thing you want to be concerned with the surface modeler is the tolerance, and that surface tolerance is based upon how dense your point cloud is. And you can play with that and tweak it depending on your data. And then in the other side, applying the raster, you have the appearance setter. And this is another, just drop it into the workspace. It should come up with pretty much all the settings we want. The only things to be aware of is that we want to set the appearance on the front side of our little triangles that we have for our tin surface. And then we want to drop the texture mapping top-down geo-referenced. And then the digital surface model, which is basically the same thing that we had before, the entire point cloud, but we're taking away all the vegetation, all the buildings. And the key to this is the point cloud filter. So we can filter out everything that we don't want, or we can filter out multiple things, or you could just have vegetation or vegetation in buildings. And this allows us to dig down into what we want and only show the things that we want for our model. And then non-classified data. Most data will be classified when you get it, but if you do get data that isn't classified, you can use the point cloud expression evaluator to run expressions that would fit your data. So for this one, we're basically going to compare it to itself and try to find the base or the surface model of it. And you can see it's only 3 transformers here to be able to do that. So there's a lot of different ways which you can interact with your data and pull out what you want manually. And then there's all these nice tools like the LAStools where you can do it a little more quickly and potentially with more accuracy. But Kaylin will talk about some of these transformers later on. So for the second part of the demo, I just want to show FME server. So with FME server, I had the geometry picker on the front end of that workflow, and that just popped in the JSON. And when I put it up to FME server, I get the choice of a little dialog. So if I have a really big point cloud, I can cut out a small area of it. I can zoom in, clear it, create a section of it. And then I've got options down here. Do I want a digital terrain model or a digital elevation model? And we'll run it. And this will bring the data right back to the user. The other nice thing about FME server is typically we have quite a few engines on there. So if your workflow is really big, there are ways where you can read in specific tiles and then have those processed on individual engines. So each individual engine will process a workflow. So if each one is running just a small subset of that point cloud, you can process things a lot quicker. So now we've got the data download URL, you just download it, and then you can open the file and you get your point cloud digital elevation model from the point cloud. So this is a nice way where you can take your workflows and make them quicker or self-serve, or you can speed them up with dynamic engines. You can automate them. LiDAR, presumably your data sources would be very similar coming in, so you should be able to apply the process to many things, and you can take it out of your hands and you can focus on building or doing more interesting things with your data if you have a flow that you need to do on a regular basis. The big FME server installations, or if you have, again, multiple engines or lots of RAM, it can really help speed up these big processes. And that's it from me. And we're going to pass it back off to Jovita now, who's going to look at the city modeling.
So our next part is looking at visualizing solutions by using LiDAR for 3D city modeling. We're going to build upon what Kaylin and Richard talked about, and we're going to put those elements together to make a slightly larger workflow that creates that kind of 3D visualization as an output. The goal of this workspace is to integrate data from a variety of sources in order to create an enriched visualization of the city in 3D. And that can then be used to inform decision making in uses like planning and development. And we're going to overcome all these obstacles of different various data sources and formats by using FME to extract the information we need from LiDAR and create that visualization. So before I get actually into the workspace, I want to talk about my inputs because I've got quite a few here. First off, I'll be using AutoCAD DWG, and those are the pink outlines that you can see of the building polygons. I'll be using point cloud, the LAS format, and this is a section of the City of Vancouver. So a lot of this data is from City of Vancouver's open data portal. And this is just a small section of the City of Vancouver around the Granville Island area, if anyone is familiar with it. And that's just the Fraser River, I believe, or False Creek, right in the middle there. I've got map info as well for my park polygons, and that'll be because I'll be working with a tree model, a 3D SketchUp tree model. And so I just wanted to limit to a certain park just for rendering for this demo. And then finally, I've got 4 GeoTIFF images or ortho images, and they're just tiled images that I've selected for this area. So it's a little bit larger, and I'll be clipping that down. And then the 3D SketchUp model that I mentioned of that tree that we'll be replacing points with, and finally a texture image for the walls. So this isn't exactly representative of all of Vancouver's buildings, but if you imagined every building as, if anyone's familiar with UBC's buildings, Ponderosa, then the whole city is now Ponderosa buildings. So I've got 3 goals for this workspace. The first is to create 3D buildings using the point cloud and the DWG outlines, where we're going to extrude the outlines to the height of the building using that LiDAR information. Next, I want to add PNG and ortho photos, so the GeoTIFFs, as textures to the 3D models. We'll be using that wall texture for the building walls and the ortho image for the roof. And the third output that I want is to filter data to get point features of trees and replace them with instances of a 3D tree model. So in a particular park, I think I had selected Granville Loop Park, I'm going to change the tree points into 3D models, the same instance or different instances of the same definition of a model. So with that, we're going to head into the workspace. So once again, I'm going to go over the inputs and the outputs first, and then I'm going to go through this bookmark by bookmark to show what we're achieving. I've also got targeted inspectors in my workspace so I can view outputs at strategic places. So starting off, I've got my outlines, building outlines in DWG, my point cloud right up here. Scrolling down to this green bookmark, I've got my point cloud again, and my SketchUp tree model. And usually I really personally just like to have all my readers on the left side here, but it made sense for me to have my textures on this yellow bookmark. So I've got my JPEG of the wall texture and the GeoTIFF. So let's start off in the first bookmark. think I'm going to use the zoom feature. There we go. In this blue bookmark here, what is happening is, I'm going to select this while I'm waiting. What's happening is that we're taking the building outlines and we're taking the point cloud and we're extruding the building outline to the height of the point cloud. And in this workspace, some of the bookmarks are collapsed. And what's happening in those ones is that we're getting the base height of the building from the terrain all the way to the top of the building to get the actual height of the building itself. Turning all of these off, and I want to see extruded buildings and tin surface. Extruded buildings. And this is just in the visual previewer here, so I'll make that a little bit bigger. So at this point, at the end of this blue bookmark, what we've got is our 3D buildings and terrain. So that's well and exciting, but we could do more with this. We will head into our next bookmark. In this green bookmark here, what's happening is that we're adding the orthophoto terrain appearance to the terrain, and that's something you've already seen both Kaylin and Richard do, and this is just using an appearance setter. Next, we are separating the walls from the roofs. We want these different surfaces so we can apply different textures to them. So out of this output, what's important is test filter for the wall and the roof, and we're using planarity filter to separate, to make the differences between wall and roof. In this yellow bookmark, we're finally applying the wall texture and the orthophoto. And once again, we're just using the appearance setter and an extra clipper in order to make sure that those images are fitting within those building footprints or building outlines. And we can take a look at the wall texture and the roof texture. As you see, when I select on one of them, it gives me all of them that I have on my canvas. Roof texture, wall texture. Take a closer look. So in this case, I did apply the same texture to all of the buildings, but you could take this a lot farther and say, for buildings of this height threshold, I want to use this texture, or for every 5th building that comes through, I want to use this texture, and you can vary it up a little bit and have smaller buildings with maybe more house-like textures. So you can see some of the greenery on some of these buildings, as well as the wall texture. Making that small again. And then finally, the last bookmark here, what we're doing is, and I'd like to zoom in a little bit farther, what we're doing is taking the point cloud and the SketchUp tree, and there's an article in the community for getting boundary features. They're not the exact tree points, they're kind of interpolated from kind of stands of trees and then having a center point replacer in order to get sort of a visualization of what that area looks like. And we're replacing those points in the Granville Loop Park, and I did 5 for a maximum just for this demo, and writing out to GeoDatabase as a multi-patch. So I had said I was going to talk about the readers and the writers. In this particular instance, at the end of really any transformer here, the data is ready to write out. I did see a question about the point cloud combiner and whether that data was kind of virtual or if like that's ready to write out. And it is data that's transformed and ready to write into the format you need, so long as that target format supports it. And I have zoomed in very close. Let's go back to 4. So the outputs in this particular workspace are to Cesium and to file geodatabase. It really could be either, and I just wanted to show that you could integrate different sources and then write out to multiple formats at the same time. And oops, excuse me, I don't use the zoom function very much. There we go. So this is my Cesium writer, and in this particular workspace, I'm just writing my buildings and my buildings to Cesium. So we can go take a look there. I have my node server turned on, and we're going to head into Cesium. I'll just rerun that. So as you can see, we have of course I reran it, which is a great time to do so. We've got our 3D buildings and the wall textures as well as the roof textures. And of course I could take this a step farther to make sure it's actually on the earth, but this is what we've got here in cesium. So with that, I will head back into the slides. And that was just a quick screenshot. So the workspace highlights. I had mentioned that there was an article for the tree instances. There's also some how-to articles on building 3D buildings using point cloud and vector building outlines, as well as for getting a boundary feature from point cloud. So there is an article on creating, if you don't have that vector layer, that you could create the buildings. They just don't look quite as clean and snappy. That's something that you could try out. Some tips and tricks on the methods for working with LiDAR are its similarities to raster processing. You're able to tile large data sets similar to rasters and just work through those in chunks, as Richard had said. And you can use feature caching strategically. So in my particular workspace, I've turned off feature caching, but there are instances when a transformer or a process is quite computationally expensive that you might want to just run that one time and have it cached so you can use it again later without running it again and again. And what we recommend for that is to use a junction. So if you're not sure, it does take a little bit more knowledge to know what transformers are computationally expensive or perhaps are affected by or work differently during runtime, and that it stores something kind of temporarily that changes each time it's run. So just kind of for best practice, you can add a junction after the point that you want to be able to view, and then you can view that junction each time. Secondly, knowing how FME works with point clouds is really important. I think we've touched on this a little bit already, that FME is a geometry in it. Oh, sorry, FME is not a geometry. Point clouds are a geometry in FME, and they're considered a single entity. So you got to look at what format you're writing to, such as if it's a shapefile and you're writing a point cloud to a shapefile that doesn't support point clouds, it's going to write out a boundary polygon of the LiDAR extent. So be sure to know that we have transformers to coerce it to the correct geometry, such as multi-points, or to a surface or to a raster, and that you're looking at what the target format requires. Lastly, kind of jumping backwards, there's lots of operations that are point cloud specific, such as working with attributes versus components. So check out the point cloud transformers and make sure you're using kind of the correct tools for it. Such as the attribute manager will manage attributes, and then point cloud transformers can work with components. Tips and tricks for transformers. In the 3D geometry department, you've kind of already seen some of the surface creators from Richard. I've used the toon generator, which creates the surface models or the buildings, and the extruder was actually the one that created the buildings. Applying textures, I used the appearance setter to add image textures, and Richard had mentioned as well about the texture mapping type parameter, so do pay attention to that. With that, I will hand this back to Kaylin.
Awesome. Thanks, Jovita. Kaylin, I'm going to pass it your way. Before I do that, I'll mention there was a question that was asking whether or not you were going to get access to the workspaces. And yes, we are going to share out everything we can. So you can check your emails for that.
So this brings us to our final step of expanding your toolset with the FME Hub and third-party tools. So here I just chose a few different point cloud transformers from the FME Hub to highlight, and we're gonna just walk through them. So if you can recall, I did demonstrate the point cloud thinner, so our in-house thinner, and this one's a little bit different. The hint's kind of in the name where it has the spatial. And so it's a bit more spatially advanced than our in-house thinner, which if you remember samples points on an interval or by set. So our in-house thinner is more or less like a glorified sampler. And so the spatial thinner is a little different where it makes sure that 2 points can exist in the same interval or cell so that they have to be a certain distance or resolution apart. And so this is really good if you're doing something where you need more control over your points. For example, if you're filtering data before generating a raster DEM, you can set the thinning resolution to be the same as the raster cell size. If you wanted to keep it with in-house transformers and you didn't want to use the spatial thinner, we also have the point cloud simplifier, which is a little bit more geometrically advanced. And it does thinning, but it aims to preserve the original shape of the point cloud through the use of different algorithms and transformations. I don't recall what algorithms we kind of have built in there, but it is in our documentation if you wanted to take a look. And so this top point cloud is our original, and then the bottom one is the thinned. And so here I've thinned this at 0.25 resolution, and the colors of the point cloud are different. So we color point clouds between this top one and the bottom one between a range of lowest blue and then the highest values being red. And these are typically pulled from the point cloud header. So here we can see they're being recolored because we're actually changing the amount of points. So we're changing the range at which the values are. So from here, I'm going to jump into FME Workbench, and I'm going to show you just the difference at running it at 0.3 resolution. So when we're running it at a 0.25, which you can see that's the only parameter we have, we can see about 350,000 removed. And then if we run it at 0.3, my plan originally was to walk through this with you guys. I was just a little bit hesitant for rendering. We can see another about 30 to 40,000 points removed, and we can check this out by going here. So we can just see that we have this many points and then at 0.25. So you'll notice in my screen, in my slide here, this is a teal color, and then in my workspace, this is a green color. And so that's the difference between a embedded and a linked transformer. So all I've done is gone ahead and embedded the transformer. So if you right click, you should see right under edit, it should say embed. And then this will allow you to actually open it up right in your workbench. So here we can see kind of behind the scenes what this is doing. You can see it groups by the cell. So that's how they kind of maintain the resolution. And then they just have a point cloud merger to kind of reset all the components and rebuild everything. And we can hop back into the slides. So the next FME hub transformer is the point cloud stats rasterizer. And this replaces a point cloud with a one band raster. So you can input a point cloud and then you're resulting a band 0 raster. And so really what this does is it stores all the statistics and all the information from your point cloud and it stores it onto the raster directly. And so we're going to walk through a demo. This is good when you're kind of newer to working with point clouds and rasters and you're looking for that easy kind of transition between formats. And so what I did here is I just added a raster palette to kind of give it a nicer look. And so again, I was going to walk through this and build this with you guys. But again, for rendering, I wasn't really willing to risk it. So this says a XYZ point cloud. It was a LAS, I just converted it for something different. And then we're gonna go through the stats rasterizer. I left all parameters as default. Again, depending on what data you're using, you may need to change these. And so from here, we can inspect this cache and we can see this is our resulting raster. So if you wanted to kind of do some raster processing on this further, we do have other resources that we can link out. And so all we're doing here is we're coercing the type to be UN8 so that it can support a raster palette. And then we're using an attribute file reader to grab the palette. And it's being stored in file contents. Kind of just looks like a whole bunch of nothing, but I can actually show you the palette itself. So this is all the palette is. It's just taking RGB values. And then these are just HTML RGB color codes. And I'm probably gonna have to close that. And then we're using the raster palette adder to add it to the palette. And you can see that this is our resulting raster. And the palette should be, should show up down there. The last FME hub transformers or tools I'm going to go over is the LAStools. So the LAStools is a collection of highly efficient batch scriptable multi-core command line tools. And so they have tools to classify, tile, convert, filter, raster, triangulate, polygonize. They have a lot of tools. And so these tools are meant for high speed, low memory, seamless processing for point cloud data. And here I'm gonna run through this workflow, and I'm gonna set you up to use LASClassify, but I'm not going to run it myself. And so we can start out with LASGround. So first things first, with any workflow, we're just gonna read in our data. And I've assigned a coordinate system. So this is coming from the city of Coquitlam, and it's a UTM 83. And so if you notice in the data inspector, we have the classification already set as a component. And so that's something that we're going to want to remove because we're going to want to reclassify it ourselves. So typically, if you're downloading city data, it's likely will have already gone through the noise removal and classification process. So those are some things to keep in mind. So to remove the classification, we can add a point cloud component remover. You just select the classification as the component to remove, and then after your output should not have a classification component. This also comes in handy if you're merging two different rasters or point clouds, sorry, with different classifications, perhaps for the same area. So you could remove the classification of one and then merge and reclassify the other half. So from here, now we can jump into LASGround. So LASGround is a tool for bare earth extraction or identification, and it pretty much classifies LiDAR points into ground points as a class 2. You'll see here I changed the horizontal and vertical units from feet to meters because of our coordinate system. So that's something to keep in mind. And then you can see after running this tool, all the ground points are classified as 2. Excuse me. So LAStools is a suite of transformers that needs to be run in a particular order. And running LASHeight kind of requires that ground points have already been classified. So so this assumes that ground points have already been classified as ground points, and now they can be identified to construct the tin, which is how they do the math of height above ground. So by default, the resulting heights are quantified, as you can see. You can store these as in user data, or you can store it as a component. For the screenshots, I stored it as a component just so I could quickly show you guys. And yeah, so now after running this, now that you have your LASGrounds, you have your ground points, and then you have everything set up for your tin, you can go ahead and run your LASClassify. Some tips and tricks: definitely run with feature caching off if you can. I know that makes it a little bit harder to compare your results. Also, if possible, try running these tools from the command line. I think it's a little more seamless that way. And if you are running into these errors when you're running your tools and you're kind of at a loss, try purging your temp folder. That's something I found that worked. I ended up having to purge after every tool when running with feature caching. And I also decided that if you shorten the path, you kind of get a little bit quicker results. I used to have a crazy long user path in here, and shortening it up kind of improved performance a little bit for me. Okay, I think Richard is going to wrap us up.
Okay, thanks, Kaylin. So to wrap things up here, we want to just talk about, reiterate the fact that when you're authoring your workflow or you're pushing it up to production, that there's different ways to deal with your data, clipping it, thinning it, using the feature caching or not. And there's a lot of tools to make it really accessible and usable by the user, and you don't have to worry about it. When we're looking at our LiDAR data, this is just a recap of everything we went through. We went through a lot of transformers, and I really wanted to focus on the fact that it can get complex and it can get detailed and nuanced, but you can also just use a few transformers to get more value out of it. It's very easy to get started with your LiDAR data. There's also a good use case for FME, just being able to prepare your data, to clean it up, to thin it out, to make it usable from other applications. We also want to highlight how FME Server, part of the whole platform, can take these workflows and really speed them up or automate them or allow you to do self-serve options. Lastly, there's visualization of surface models and city modeling. They can really help add value to your data. And lastly, FME includes this third-party tool set, the LAStools, which can provide a lot of detail and a whole new range of tools for you to use. So you can get deep dives into your point cloud data if you're interested. So you claim your badge. We have badges for just watching this webinar. We'll send this all out afterwards, so you can go to the link and enter your code and you can get a badge. And that's it from us. So we'll be answering some questions if you have any and want to hang around for a little bit more.